So our next speaker is Surya Ganguli. So Surya actually has a background in physics. He did his PhD in string theory, and he spent some time working at UCSF in neurology, and now he's assistant professor at Stanford in applied physics. So Surya does a lot of interesting work. I'm trying to understand the brain, in particular things like memory, using tools from statistical mechanics and systems. And recently he's been also interested in understanding what deep networks are actually doing. So hopefully he'll tell us a little bit more about that.
So I'm going to talk about some results in non-convexity, both in the error landscape and also the expressive capacity of deep neural networks. And I'll show that there's a connection between expressive capacity and of course, the difficulty of optimization due to non-convexity. So I just wanted to review some work which is now old because it's a year or two old. But this is where we kind of started from. So of course it's often thought that local minima and high error stand as a major impediment to non-convex optimization. And indeed, if you draw an error landscape over a low-dimensional space, this is a cartoon of a protein folding landscape, it can be riddled with local minima and high error compared to the global minimum. But it turns out random non-convex error surfaces over high-dimensional spaces, local minima and high error are exponentially rare in the dimensionality, instead saddle points proliferate. And we developed at least one algorithm that rapidly escapes those saddle points. And so this is work that was reported here, and Anna Kromanska and colleagues have also done related work using a different perspective, a mapping to a different physical system. But they have largely similar conclusions. So the way that we approached it is we don't really understand the error landscape of deep neural networks, so let's just think about generic properties of what occurs in high-dimensional spaces. And this was worked out by a pair of physicists in Physical Review Letters 2007. And they looked at the following. So consider a random Gaussian error landscape over n variables. So you have a scalar function over n variables. If you evaluate the scalar function at any 2 points, they're jointly Gaussian distributed. So it's a single draw from a Gaussian process. That's your error landscape. There's no other structure in it other than smoothness. Now, that will generically have many, many critical points. So let x be a critical point where the gradient vanishes. You can plot every single critical point in a two-dimensional feature space. One axis of that feature space is the error level of the critical point. So that's this axis. And then f is a fraction of negative curvature directions, a fraction of negative eigenvalues of the Hessian at the critical point. A priori critical points could appear anywhere in this two-dimensional feature space, but it turns out, at least for this ensemble of error landscapes, there's a concentration of measure phenomenon where they concentrated on a monotonically increasing curve. The global minimum is here at lowest error, the fraction of negative eigenvalues is 0. Here's the global maximum, highest error, and fraction of negative eigenvalues is 1. And they concentrate on this monotonically increasing curve such that the higher the error level of the critical point, the more the negative curvature directions. This has two major implications. There are no local minima at high error. That's this region, it's forbidden. And two, if your local minimum, your error level is close to that of the global minimum. Okay, now as physicists, we're kind of used to the notion of universality, which is that there are certain questions that have answers that don't depend on the details. So for example, what often happens is there are certain questions whose answers only depend on the symmetry of the problem and the dimensionality of the problem. So for any generic error landscape in high dimension, you expect this kind of a qualitative feature to hold. Of course, computer scientists are not as used to the notion of universality, and they might say something like, no, the error landscapes over our deep networks are very, very special. They're very, very different. They have a lot of structure that is different from what you see in these Gaussian landscapes. And that may be true in many different ways, but it may be that if you ask the same question, you'll get the same answer because, again, of universality. So that was my physicist's expectation. And so we collaborated with Yoshio Bengio to test exactly this prediction. So this kind of just started when Yoshio invited me to come and give a talk in Montreal. So we tested exactly this. We used Newton's method to search for critical points, and Newton's method gets attracted to critical points of any index. And so this is the fraction of negative eigenvalues, and this is the error level. This is the error landscape over a deep neural network exposed to training data from MNIPS. And this is for a deep neural network with CFAR10 training data, a classification problem. And you see that there is this monotonically increasing curve. So it's qualitatively consistent with the statistical physics theory of random landscapes. Okay, so again, there's no local minimum high error, and if you're a local minimum, your error level is close to that of the global moon, at least as far as Newton's method can sample these things. Okay, but what can we do about this? So why is Newton's method attracted to critical points of any index? Well, Newton's method is a gradient step weighted by the inverse Hessian. Right? So if you're in a direction when the eigenvalue of the Hessian is positive, that's great, you go downhill. However, if there's an eigenvalue that's negative, that introduces an additional negative sign that turns you uphill. Okay, so an extremely simple fix is just to divide by the absolute value of the Hessian, where by that I mean a matrix that has the same eigenvectors as the Hessian, but all its eigenvalues are replaced by their absolute value. That fixes this problem. And it turns out you'll go downhill. And you'll descend rapidly even if there are flat curvature directions. So saddle points repel Newton's methods. We call it saddle for Newton's method. There's actually a derivation that makes this make sense away from saddle points. And the basic idea is you minimize a linear approximation to f of x within a trust region determined by when the linear and quadratic approximations agree. So basically you don't use the quadratic information to approximate the model. Because the whole idea about Newton's method is it descends a positive definite quadratic pole in one step. But if positive definiteness of the Hessian is a horrible local model in generic high-dimensional non-convex problems, you don't want to use the quadratic information to approximate your function. Instead, you do a linear approximation because you can always trust that. And you use the quadratic information to determine the boundary of your trust region. And then this falls out as an approximate version of this thing. So I know Nando gave a talk here. Unfortunately, I couldn't make it because I had to talk somewhere else. But he has a talk on learning to learn. But it's kind of interesting. Maybe what's also important is learning to trust, right? We should try to figure out when we should trust how far we should go. And if you could learn how to trust, that might be a very interesting direction for future research. How well does this work? These are learning curves for stochastic gradient descent for a deep autoencoder problem and also a recurrent neural network problem. And so stochastic gradient descent, the learning slows down and it sort of flattens out. But if you switch at that point to the saddle-free-Newton's method, the learning curve suddenly drops again. So this plateau was an illusion of a local minimum. It was actually the fact that the stochastic gradient descent got slowed down but not stopped near a saddle point, and it needed to go down negative curvature directions that were not that curved. We did some other simulations where we checked that whenever there was a sudden drop in the saddle-free-Newton method, there was a sudden rise in the negative curvature eigenvalues of Hessian. Okay, so now what I'd like to talk about next, this is more recent work, is where are all these saddle points coming from? Just in a generic network. Can we obtain kind of a geometric picture of what's going on? And what I'll show you is that we can connect the prevalence of these saddle points to the theory of chaos in the following sense. Okay, so just imagine a generic deep neural network. There's three important things: the input x, the output y, and the weights, which parameterize the function. Right? So let's imagine what the error landscape looks like for squared loss, just geometrically. So for each set of weights, I have a point in function space, which assigns for any set of inputs a set of outputs. This is an infinite dimensional function space, but let's truncate to finite dimension by considering a finite set of inputs, say p inputs. Then function space is determined by the values of the outputs on each of the p inputs, so y1 through yp. So this is now a finite dimensional space restricted because we restrict to a finite set of inputs. Let's say that those inputs are the training data. Okay, so now as you vary the weights, you will trace out some volume or some manifold in function space. Okay, so that's a holistic view of the set of functions that are realizable by varying the weights of your deep neural network. It will generically be some complicated manifold which we would like to understand. The training data is a single point in function space. It's basically the outputs for each of the training inputs. So that's a single point. And if you're using squared loss, for example, of the output, then geometrically the error surface is just Euclidean distance from the training data to each point in function space. It's a scalar function on this manifold. So any kind of saddle points in the manifolds traced out by function space will turn out to be saddle points in the error landscape, just because of this geometric picture. So the geometry of function space is incredibly important in understanding the structure of the error landscape. Now it turns out, as we'll see, there's a phenomenon that occurs in even these feed-forward networks, which is called weight, which I call weight chaos, which is a small change in W can lead to a large convoluted motion in function space. So that this manifold is a highly corrugated manifold, it turns out. Okay, a dual view of that is input-output chaos, which is that a small change in X can yield a large change in Y. These two phenomena are in some sense dual to each other, inseparable from each other, because of the structure of the way we compute in these neural networks. The weights are always dual to the inputs, and you're always taking dot product between weights and inputs. So if there's chaos in weight space, then there's also input-output chaos. Okay. Now next, I'm going to switch gears, and I'm going to talk about the expressivity of neural networks. Neural networks deep neural networks. So a natural question to ask is, what can deep neural networks express that shallow networks cannot? That's the expressivity problem. It turns out we can show that the expressivity of deep neural networks can originate from input-output chaos. And then by the considerations that I've talked about intuitively now, but can be made much more mathematically precise. As a concomitant effect, you get weight chaos. And so expressivity comes hand in hand with difficulty of trivial. Now, it turns out these ideas of weight chaos were actually studied back in the 80s and 90s in the context of spin glasses. So there's something called temperature disorder in spin glasses, where a spin glass is like a Boltzmann machine that assigns energies to multiple spin configurations. And if you change the temperature slightly, what were the low energy states completely become high energy states, and what were high energy states become low energy states. So there's a huge reshuffling of states. And this work is kind of inspired by that. It turns out the same weight chaos that holds in spin glasses also holds in deep neural networks. Okay, but the way we get at this is through the problem of expressivity. And so I'm going to connect to a different problem, a different motivation, but for the purposes of this workshop, it connects to the error landscape through this connection between input-output chaos and weight chaos. So what is the expressivity problem? It's basically, in a nutshell, what kinds of functions can a deep network express that shallow networks cannot? This was presented at NIPS this year, and there's a sort of a companion paper that's under review. This is work done by, so Ben Poole was kind of the ringleader of this project. He did all of the simulations. Shubhani Mahir is my postdoc. It was sort of a collaboration with Maitra and Joshua at Google Brain. So of course, a natural question is, why do we even need deep networks given the universal function approximation theorem? So neural networks with one hidden layer are universal function approximators, so why do we need depth? Well, oftentimes for the functions we want to compute, or generic functions, we don't often have guarantees on how many neurons you need to compute that particular function. For certain classes, you do have guarantees, but in general, it's hard to place such guarantees in the size of the one hidden layer. And the overall idea that has a long intellectual tradition is that there exists certain potentially special functions that can be computed efficiently using a deep network, i.e. polynomially the number of neurons in the input dimension, but not by a shallow network, i.e. it may require an exponential number of neurons. And this idea has intellectual traditions in Boolean circuit theory. For example, the parity function is such a function for Boolean circuits where logical depth replaces the number of layers. So there's been a lot of work on exhibiting such special functions. And they've relied on very specific theoretical techniques which are tailor-made for specific nonlinearities and specific measures of functional complexity. So for example, Bengio and Montefort and colleagues showed that for ReLU networks, the number of linear regions for a particular function can grow exponentially with depth, but not with width. For some product networks, it's the number of monomials compute, because some product networks compute polynomials as the number of monomials. And here these guys use algebraic topology. But if this is a very generic phenomenon, we should have a much more general theory that doesn't rely on rigidity in particular theoretical techniques to attain results. In fact, the type of rigidity we'd like to remove is we'd like to come up with a theory that applies to arbitrary nonlinearities. So the way we're going to do that is we're going to really think geometrically about what's going on. Similar to the, this will be required to think about the geometry of function space. Okay, so we're going to actually use Riemannian geometry and ideas from dynamical mean field theory and physics. We're going to combine them to show that the curvature, the extrinsic curvature of functions computed by deep networks can grow exponentially with depth, but not with width. Okay, and moreover, the origins of this exponential growth can be traced to the theory of chaos. So the theory of chaos is actually a subset of the theory of deep networks. Okay. I'm going to skip this for now, but we can also talk about disentangling. The decision boundaries of classifier networks in the input space can be highly curved manifolds whose curvature grows exponentially in depth in a way that we can mathematically formalize to the point where we can actually quantitatively assess this idea. So the idea that deep networks disentangle neural representations has been sort of long captured the imagination of both neuroscientists and machine learning people, and we can now quantify this and assess it, but I'll skip that. So how are we going to do this? What we're going to show is that if you give me a random deep network, I'm going to show you that it can do something that no shallow network with one hidden layer can do. So we're going to analyze a maximum entropy distribution over random deep networks to show that our results are sort of robust and are a property of depth alone and not particular choices of structure in the weights. So the ensemble of so this is the dynamics of the network. So you have inputs to a neuron that go through a pointwise nonlinearity, and you have linear summation from the previous layer. So this is standard neural network dynamics. We're going to choose the weights to be IID from a Gaussian distribution. I'm going to scale the variance of the Gaussian distribution to be 1 over the integrity, so that as the width goes to infinity, this ensemble has a well-defined limit. And the biases will be order 1, so they compete on the same footing as the weights. So the biases are also IID from some distribution. The important parameters of the distribution are the variance of the weights and the variance of the biases, and they interplay against each other in an interesting way. Okay, well, the basic questions I'd like to ask are, how does a single pattern propagate through the network? So a single point is like a pattern of activity across neurons in the input layer. It's a point in this n-dimensional space. Its length can either grow or shrink as it propagates through the system. But more importantly, a pair of points, if I put in two patterns in the system, two input patterns in the system, do they become more correlated over the layers, or do they become more decorrelated over the layers? That's the second question I'd like to ask. Then a smooth manifold, if I propagate a smooth manifold through the system, how does its curvature and volume change? Okay, just because it's a shorter talk, I'm going to skip the details of a single point and go directly to 2 points and tell you the answer. So what we find in the system is we find a phase transition. For sigmoidal nonlinearities, we find for tangent nonlinearity, we find a phase transition here. Let me just give you the definition. So let's say that I have 2 points, 2 patterns in the network. So 2 input patterns here propagate through the system. They form an internal representation, HL, for pattern A and pattern B. I can look at the inner product between these 2 input representations. In particular, I can look at the correlation coefficient between them. And we can write down a dynamical theory for this, an analytical theory for this correlation coefficient in terms of a set of recursion relations. The theory matches experiments really well. So this is how the correlation coefficient evolves with depth. The solid curves are the theory. The dots and the error bars are numerical simulations of networks of width of 500 and various depths. And as you can see, our theory matches numerical simulations very, very well. The fluctuations are order 1 over the width, so we expect it to match well. But how does it actually behave? So remember, these are the 2 important parameters in our ensemble, the standard deviation of the biases and the standard deviation of the weights. There's a phase transition in this plane, where if the biases are very strong, but the weights are weak, then the biases tend to align inputs in an input-dependent manner. All the inputs will follow the biases, and any 2 inputs will become the same. And the correlation coefficient, which is shown here on this heat map, will be driven to 1. However, if the weights become larger, then what happens is the weights will expand. The large weights will expand the inputs, and the nonlinearity will fold space. So that iterative expansion and folding will cause 2 similar inputs to decorrelate over time as they propagate through the system. So that's basically the intuition. And for the large weight regime, you get decorrelation between points. For the small weight regime, you get correlation between pairs of points. Okay, now this has implications for the propagation of manifolds through the network. And now we're going to get to input-output chaos. So now let's imagine that we just have a simple one-dimensional manifold propagating through the network. Everything I say holds for higher dimensional manifolds as well. But let's say we just pick a circle sitting in a randomly oriented 2-dimensional plane. hiding within or set within this input space. And we let it propagate through the system. Okay. We can measure, so theta is some coordinate on the circle. Theta 1 and theta 2 are 2 points on the circle. These 2 points will create 2 internal representations up here. And I can look at the inner product between those 2 representations. It's the same thing that we did for 2 points, but now it's a function. And in particular, I can look at the autocorrelation, sort of, if I move a distance delta theta, how quickly does the correlation between the internal representations of those 2 points fall off, average over the circle. So we can look at that. And great. So here are just simulations of what goes on. So so this is small weights, intermediate weights, sigma w is larger, and here's the sigma w is larger. So this is the ordered regime where you get correlation. This is a disordered regime where you get decorrelation. And just the principal components of visualization of the circle just shows intuitively that in the chaotic regime, the circle is getting more and more ruffled. Okay. Whereas in the ordered regime, it largely remains a circle because you're not really exploring the nonlinearities because your weights are small. Okay, you can see the same thing in terms of autocorrelations. The autocorrelations become narrower and narrower as you propagate through depth. Okay, now the question is, what's actually going on here? It looks like the radius of curvature of the circle is tightening with depth. Okay, the first surprise of our work is that that's actually a total illusion. It's an artifact of dimensionality reduction. Now this is PCA, so lest you think it's an artifact of linear dimensionality reduction, I want to assure you it's not. If we use TC, then we see the same thing. We see, so this is in the chaotic regime propagating through the various depths. The radius of curvature of the circle under TC plots is also tightening with depth. But again, I want to show you that that's an illusion and there's something very different going on in these networks. So we have to confront the geometry of this manifold directly in the high dimensional space without doing dimensionality reduction. So we want to use ideas from Riemannian geometry to quantify the geometry of this thing. So the first one is length. So, we know about Euclidean metrics. We can compute the length of the curve in the high dimensional space. I won't belabor these definitions. The next one is curvature. So what is curvature of a curve? So if you have a curve, there's 2 special vectors at any point. There's the velocity vector, which is a tangent vector of the curve, and there's the acceleration vector. These two vectors give you a 2-dimensional plane. Within that 2-dimensional plane, there's a unique circle of some radius that has the same velocity and acceleration as the curve. That's called the osculating circle. The 1 over the radius of that circle is the extrinsic curvature of that curve. So this is an order parameter that doesn't depend on coordinate systems. It's invariant with respect to coordinate systems. And this is an explicit formula for this extrinsic curvature measure. There's also something called Riemannian length, which is how far it moves under the Gauss map, but let's ignore that. Now let's imagine how the curvature of a circle changes under a simple transformation to get into it. Let's say that you just have a circle and you linearly expand it. What happens to the length and what happens to the curvature? Let's say the expansion factor is chi1. Okay, if chi1 is bigger than 1, you get expansion, so the length becomes bigger, but the radius becomes bigger, and curvature is 1 over radius of curvature, so the curvature becomes smaller. So linear expansion does 2 things. It lengthens out the curve, but it sacrifices curvature. What I'm going to show you is that deep neural networks do something qualitatively different. They will expand length without sacrificing curvature. And that happens because of the curvature and the nonlinearity. The way we show that is, again, we derive analytical recursion relations from the propagation of Riemannian geometry, in particular extrinsic curvature through the network. And what we find is we find a leaky integrator of curvature. So this is the curvature that's present in layer L-1. And this is kind of the expansion factor. This expansion factor is bigger than 1 in the decorrelating regime because it locally expands space. And so clearly, if you expand space, you attenuate any existing curvature in the previous layer. However, you're also propagating through a nonlinearity, which itself introduces new curvature. It turns out that it introduces it additively. Okay. So then what's going on is the linear expansion attenuates curvature in the previous layer. The nonlinearity introduces curvature, And this is like a leaky integrator, so it settles to a fixed point as you propagate through depth. This chi2 factor is just the average second derivative of the nonlinearity, it turns out. So this predicts that the extrinsic curvature, and therefore the radius of curvature, should go to a fixed point. Okay? That's kind of surprising. That's counterintuitive, or that's actually the right answer, and the low-dimensional visualizations are counterintuitive. But the length, the metric, actually grows exponentially in the chaotic regime. So what's happening is, the network is expanding and folding, expanding and folding. So the circle is getting expanded to a big piece of spaghetti that has a constant radius of curvature, but twists and turns exponentially many times with depth. Okay. So that's actually what's going on. These plots, which I don't have time to go into, are theory and simulations, and they match perfectly. Now, the other thing, we prove a deterministic theorem that shows that if you just have a shallow network, the length can at most grow as the square root of the width. So any random deep network can do what no shallow network can do. It doesn't matter how you choose the weights of the shallow network. Okay, so let's skip that, the disentangling. So again, what are the implications? So remember, everything I said about input-output chaos also holds for weight chaos. Okay, so if input manifolds propagate and become decorrelated in output space, then as you move in weight space, function space becomes decorrelated. Where you move to in function space becomes rapidly decorrelated from where you were before. So some of you may have noticed that I used the same figure twice. This was a figure that I used in the beginning of the slide as a caricature of function space. But this is, I derived it from input-output chaos. But it turns out this is actually also what's going on in function space, and we can prove that. So now we have a handle in trying to visualize or geometrically understand the error landscape of weight networks by thinking about the Riemannian geometry of function space and looking at that. So that's going to be sort of future work. But again, it's intimately tied to the expressive capacity of networks. If networks were not expressive, you'd never have these saddle points, or the proliferation of them. Okay, so I'll end now. I'll just put up a summary, the text summary. Thanks.
We have time for a quick question or so. So, right,
Thank you very much. Thank you very much for very good talk. But you consider
Yeah.
so where this results from slave case where you consider and also where
Yeah, so that again boils down to universality. As long as the variance of the weights are large, I would expect it to hold. And we've done some simulations and we see it there. The position of the phase boundary is at a different place because the integrity is different and so on. But there'll still be a transition. The location of the transition is different, which is usually what happens.
So based on the fact that the transition is
Yes.